Hi everyone, welcome to another video of FIT3143 parallel computing. So in this video, we will provide you all with an example on how to use OpenMP to actually parallelize a particular algorithm. We'll be using the same algorithm which we discussed in the previous pre-lab video for POSIX threads. Okay, and we were using the same algorithm, the same problem, and this time we will parallelize it using OpenMP. So this video should be brief, and we will straight go into the code now. So I'll start sharing the screen. Okay, so looking at the screen over here, so just do a quick recap. So in the previous video, we actually covered, we actually provide a serial code on how to actually performing a cell by cell multiplication of a vector. So we have two vectors, vector A and vector B, and then we multiplied each cell, each corresponding cell of vector A with its corresponding cell in vector B, and then we stored it into vector C. So this is kind of like a Hadamard multiplication. Okay, not to be confused or mistaken with matrix to matrix or vector to vector multiplication. That is another topic which we will go into later on. But in the concept of a Hadamard application, we are taking one cell of a vector, multiplying another cell of the vector, the corresponding cell, and then storing it into a new array. In the serial code, which I discussed with you all last week, I've mentioned how we can actually compute or identify the parts of the code which can be parallelized and the parts of the code which remain in serial. From there, we compute our RS and RP fractions, and then we calculated the theoretical speed up using Amdahl's law. Some of you all asked me whether can you all use Gustafson's law. By all means, please try it out and see, and then compare. Okay, and once you understand the computational problem, then I discuss with you all on how to parallelize it using POSIX. Bear in mind, in the serial program, I intentionally added in a nested loop just to prolong the computation, because normally vector cell product using Hadamard, it's typically a fast operation. So just for the purpose of increasing the computational time, I added an intentional second loop over here. This second loop actually has no meaning at all, other than just to increase the time taken to compute the problem. Okay, based on this, then we have our parallel implementation using POSIX threads. So we are using like a fork join operation. So the part where this is the parallel code using POSIX threads. So I have a thread callback function over here. The reading from the files are all in serial. Okay, we've gone through this already. So if you have not reviewed the previous video on how to implement a parallel algorithm using POSIX threads, please review that video. It's in this. You can find this video in this channel and also in Moodle for this unit. Okay, in week 3. All right, but we are now looking at this video for week 4 as part of our pre-lab activities. All right, so now, so this is a POSIX implementation. So here at this point, okay, so what I've done, if you compare the POSIX code with the serial code, all right, I've replaced the computation here with a fork and join process, creating the threads and joining the threads. And then the writing is done in serial, and then the thread computation, each thread will execute a callback function. Each thread will execute a thread callback function. And based on the thread's unique rank value, we then compute different regions of the vector to process for each thread in parallel. And then we store the answers into an array. Okay, because this is a shared array, but each thread is writing to different portions of the array, we need not apply a mutex here. So for those of you who did the lab activity on prime search, I think some of you all implemented a mutex. Some of you all implemented some additional new creative techniques on how to bypass mutex or not. Okay, so that's pretty impressive. So there are several methods. Okay, in the context of the parallel prime algorithm for your lab activity. Okay, so by this example, there's no need to apply mutexes, because although multiple threads are writing to the same array, they're writing in different regions of the array. Okay, so for more information about arrays and pointers, I've also prepared another video which precedes this video, so you can find it in the channel also. All right, now eventually once we complete the parallelization process, we measure the time, and then we got very impressive results. Okay, we got very good speed ups. I mean, yeah, decent speed ups, and I think that was a good motivation for everyone to see how you're able to write your first parallel program for a computationally intensive application. Now, this video is then going to explain to you all how you can do the same using OpenMP. All right, so OpenMP is a different method. It's using compiler directives to actually implement parallelism, thread-based parallelism for shared memory. Okay, so we have discussed our lecture about OpenMP, and if you look at it, OpenMP and POSIX, they have the same goal to apply to implement parallelism on shared memory, but using different libraries in this context. Okay, so I've included the omp.h header file here because we'll be calling some OpenMP functions, so we need the header file to be present inside here. Okay, the main code, everything is still the same as before, so there's nothing different here. So if you're new to this code and you need some reference, please refer to the previous video on how we implemented a parallel version of this code using POSIX threads. Okay, now the part that I want to explain to you all about OpenMP is here. Okay, so there are two versions I've implemented. So I've commented on the simpler version. This is slightly a bit more tedious. So this version is similar to what we did in the POSIX threads, just that we don't have a thread function. We didn't do pthread create and things like that. What I did was I just literally copied out the thread function algorithm and pasted it inside here. But before that, I put a scope pragma OMP parallel. So what happens is, okay, so inside here, this is your main function. Okay, your main function, your main process. So your main process, first thing it does is reads the first file. It reads VA, vector A, then it reads vector B. This is all done in serial. Now, before it performs the multiplication, okay, it creates vector C using the malloc operation. And then now, at line 74, when we have the pragma OMP parallel, it will spawn n number of threads. Now, okay, now if you compare this with the POSIX example, in the POSIX example, we have specified a symbolic constant saying how many threads we want to use. All right, then in the for loop here, we did a for loop from I equals to 0, I less than num threads, and each iteration we created a thread. And then the same thing we do for a join operation. Now, when we call pragma OMP parallel, we are specifying a compiler directives. So when the compiler compiles the code, the compiler will include the OpenMP libraries, which will generate a binary. And when the program is executed at runtime, the OpenMP binaries will determine how many cores or how many logical processes are available in this system. Okay, it will determine how many logical processes are available, and based on that, it will spawn that equal number of threads. So in my case, in this particular example over here, I've set the virtual machine to run on 6 processes. So when pragma OMP parallel is executed in runtime, what happens is that you will actually get 6 threads being spawned in this particular example. If you are using 4 processes, 4 threads and equivalent. Okay, so now each thread will run in parallel. Just like POSIX, the thread functions running in parallel, each thread will run in parallel, and each thread will execute this section of code concurrently in parallel. So each thread, they will run the same instructions over here. Okay, same instructions. So that's why we can call this as single instructions, multiple data. Okay, It's not really single instruction, but single instructions, okay, or a single set of instructions with multiple data. They'll be working on different sets of data. All right, so what makes each thread unique is that the rank. So in the POSIX, when we created the thread, we have to use an array to specify the unique IDs. You pass in the address of the array location I, and that parameter is captured by the thread function over here. We dereference it, and then we get each thread will get unique rank. We don't need to do this with OpenMP. In OpenMP, we merely just need to get OMP get thread number. This is why I've included the OMP header file over here. We need to get this function, this particular thread number. This function is declared inside this header file and defined in the OpenMP library. So we need to just include the header file and call this function. So it's a predefined function for you. So we call OMP get thread number. So each thread, when they call this particular function, they will get a unique ID, a unique rank number, okay, between 0 to number of threads minus 1. And to get a number of threads, we get OMP get num thread. So be careful, it can be sometimes we might accidentally get confused or mistaken between the function name. Get thread number or get thread num, the num here is an abbreviation for number. OMP get thread num returns the ID of the thread, the current running thread. So each thread will get a unique ID. OMP get num threads returns the number of threads. Number, this one returns, okay, number of threads running in parallel, and this one returns the thread ID for each thread. Okay, so at least we are clear about these functions over here. And then based on that, we apply the same method we did in POSIX threads. And you have done it before in your lab assessment for the prime search. Okay, so rows per thread. So we are parallelizing the outer loop. So this is called a row segmentation. We do that. Then after that, we add in the remainder for the last rank, and then we compute the process. So as easy as that. Okay, so there's no need to create threads, or no need to do p-thread join or equivalent. This whole section is parallelized. So in my whiteboard, okay, so at the end they will do the entire operation over here, okay, compute, and then they will join. So there's an implicit barrier inside here. There's an implicit barrier. It's added by the compiler. Okay, there's an implicit barrier. We will wait for all the threads to finish before it returns control back to the main process. Okay, it returns control back to the main process. So there's an implicit barrier over here. And then after that, the main process writes VC to file, and then we are done, end. So we put start here. So this is a parallel operation using OpenMP. Similar to POSIX, just that the implementation is different. Okay, the implementation, how we create the threads is slightly different, but the way we do the workload distribution is similar. Okay, so now before I run further, let me first compile the serial code. Let me compile the serial code. So probably I should just, okay, so I've done this earlier on already. So what is the vector cell product .c, then -o output file. So this is the serial code compiled. Let's see the operation. So it's going to take some time. So just hang in there for a while. This is a serial operation. There's no OpenMP here. This is the original serial code. Just want to get back our processor. So you can see only at any given time, only one CPU is running. The rest are idle mode. So we are not leveraging or maximizing on our multi-core architecture on your CPU. So now remember, guys, we are still working on shared memory. We are still working on a multi-core architecture on your desktop or your laptop computers. We haven't gone into clusters yet. That is when we go into MPI later on. Okay. So we are computing now. So you can see that even though you have 6 processors available, only one CPU is working. So you're not maximizing your CPU resources. takes 35 seconds to compute, writing, and then you get total time. So from this, you can compute your RS and RP. We have discussed this in the previous video. Okay, and then we can get our theoretical speed up. So this is our baseline values. Okay, this so we take 47 seconds is our TS, serial time. All right. Okay, I'm going to skip the part where we calculate the theoretical speed up. We've done that before, so the theoretical speed up is normally calculated just to give motivation. We already have motivation already based on the previous lab video. So now I'm just going to take 47.42 as my serial time. Okay, now to run OpenMP, okay, we first need to make sure that we have OpenMP installed in the virtual machine. I mean, it is installed, but if you want to play safe, you do this only once. Okay, you do this only once. All right, you check. You copy this sudo apt-get install lib OpenMP development. You only do this once. Okay, so just copy and paste this into your terminal, or you can type it out. Oh, I don't want to delete this. I want this time. Or maybe I'll open a new terminal. Control Shift T. Okay, then Control Shift V. All right, so we run this. So if it's not installed, it will ask you to install. You say yes, and then enter the yes key, Y key for yes, and then it will install for you everything. But in this case, it's already installed, so it's fine. Okay, so we have OpenMP installed. Now, what I'm going to do is I'm going to compile the OpenMP code. So where's the OpenMP code over here? Okay, so I have my OpenMP code GCC. So to compile OpenMP, okay, you have the Pragma OMP parallel, as I mentioned earlier on already. So GCC -wall, you must specify this -f OpenMP. If you don't specify this, the compiler will ignore these directives. You'll be running a serial code. OMP get thread num will return you 1. OMP get num threads will return you 1. All this will be useless. You'll be returning a serial code. You'll be running a serial code. Sorry. So to make sure that your OpenMP is functioning, you have to compile it with -f OpenMP, and then the file name, the code name, and then -out. You can put f OpenMP at the back here, so it doesn't matter where you place it, but as long as it's mentioned inside here in the GCC compiler commands. Okay. Now enter, finish. There's no errors. Everything is good. Now let's do the fun part. Let's run the program. Let's see the out application. So technically it should be faster. So let's see comments reading. So reading is in serial. So only one CPU is working. Okay, and then compute. All right. So now all threads. Hey, something is wrong. Notice here, something is wrong. Okay, something is wrong. You only have one thread running just now. So what happened? What happened? And although your time is faster, but I think your file would not be correct. No, the file is wrong. It's supposed to be 152 megabytes. So the data is incorrect inside here. So what is wrong? What do you think probably went wrong in this example over here? Okay. Now, the thing is, notice that your I, by default, if you don't put anything shared here, by default, all variables used inside here, row 1. Okay, your myRank, numthreads, RPT, RPTR, start point, endpoint are all declared inside here. So each thread will have a local variable of this. All right, each thread will have their own variables of this. But the rows will be shared because this row 1 was declared outside of the Pragma OMP parallel construct, scope. So if you don't put shared, by default it'll be shared. So normally if you want, you can put shared just to emphasize. It's normally for your own coding reference and things like that. But if you don't put it, it's fine. Okay, but still something is not right. Okay, so the problem is this, your I and your J. Because your I and J is declared outside here, this I and J will be by default shared. So there will be a race condition here for the I and J variables between the threads. So in actuality, you should declare I and J as local variables within each thread. Or you can put integer I inside here. Okay, but but if you follow proper C, we don't normally put integer in the for loop. So you just declare integer I and j in the construct. So now integer I and j, so all of the declared variables here will be for each thread. Each thread will have their own I and j. Each thread will have their own myRank. Each thread will have their own num threads. Each thread will have their own RPT, RPTR, SP, and EP. But they will share the row one. Okay, they will share the row one. So now once we have put this I and j inside here, so let's run again. Okay, let's run again. Okay, so obviously this is wrong. Okay, our earlier one is still 47.425 seconds. Okay, so let's compile again. I've saved the code. Okay, to admit sometimes I do save a lot. Okay, okay, compile, OpenMP, running. So we'll get a warning here saying that this I and j now is unused. So that's fine. That is fine. We can just ignore the warning over here, or if you really want, we can delete the I and j over here. We don't need them anymore already. Okay, but I'll just ignore these warnings. And then I'm going to run the code now. So same thing. All right, so we have one CPU reading on the files. Now you can see all threads are running. Now this is what we wanted to see. All right, and then it's done. 7.75 seconds, writing to the file, and done. So in total, we took about 22 seconds. Okay, compared to the earlier one was not correct actually. So the earlier one is wrong because you did not prioritize your I and j. So this is wrong. Although you may think, oh, it's fast, I'm getting a good speed up, but the context is wrong. The context is wrong. Okay, so that's why you have to be very careful when you parallelize using OpenMP. You need to know what variables to be shared, what variables needs to be prioritized. Okay, these are all private variables that will remain within. That will remain. They will be unique for each thread. Each thread will have their own local copy of these variables. But the row, because the row is declared outside, is shared. But doesn't matter because we're only reading the value of rows, so that shouldn't be a problem. But for I and j, because we are incrementing the I and j, so if we didn't make I and j localized within the threads, and I and j was shared as before, or I and j was shared as before, all right, in the earlier case, then you will have a classic race condition over here. So that is why we have to make I and j as private inside here. And now we are able to get a decent speed up. 22.2 seconds is our TP time. This is our TP time. So if you remember earlier on, what is our TS time for OpenMP? Oops, sorry. Our TS time was up here. Oops. Ignore this one. This is wrong. Our TS time was 47.425 seconds. 47.425 seconds. Okay, our TS time was 47.425 seconds. Our TP is how many seconds? 22.231 seconds. 22.231 seconds. So which means seconds. Let's put SEC over here. So which means our actual speed up for 6 processors, I'm using 6 processors, is TS over TP. We substitute TS and TP with these two values over here. We will get what? We will get 47.425 divided by 22.231. This will give me an answer of, sorry, 47. Give me answer. Sorry, my bad. Arithmetic error I made just now in my calculator. Will give me an answer of 2.13. Okay, again, compared to 6 processors, it's not a very high speed up. So, but I think we discussed this before in the last video. It's due to the delays of read and write. Okay, so this is what we get. Now, this is fairly a cumbersome method. All right. Since we know that OpenMP can simplify things a lot, why not use a simpler approach rather than having to calculate our start point and end point manually? We can directly. So this is the original serial code. This is the original serial code. Nothing changed inside here. If you compare this to the original serial code, is identical. What I did was I just specify now pragma OMP parallel for. I specify private I and J, and then just for the purpose of formality, I specify what is to be shared. Okay, or I also can put here row 1. Sorry, I forgot to mention earlier on, not only row 1 was shared, P arrays num1 and 3 are all shared also. But in the earlier example, in order to make P arrays num3 and num1 and num2 private, because we are reading and writing into different parts of the array, so there's no race condition here. But the I and J has to be privatized because made in the private region, has to be made private or local region over here, because I and J is being incremented by multiple threads. Okay. So now same thing, I put pragma OMP parallel for private IJ, then the shared variables over here, and then we have the exact serial for loop over here. All right, so I save the code. Okay, I save the code, everything is saved. Now compile again, specify FOpenMP, done. Oops, compile twice, sorry. Okay. Then again, now we see the performance. One thread is reading. Reading is done. All threads are now working. Done. So it took about 7.8 seconds to complete. And then the writing takes, so you can see the time is almost identical. 7.75, 7.85. So this process is more or less similar in this context over here. Okay, and you can do a sanity test just to make sure that the contents of the multiplications are correct, but it should be correct. I've done it before earlier on already. Okay, but that's about it for OpenMP in general. I mean, there are other things like the reduction clause that we discuss in lectures, all right, and the sections clause and so forth. But those are some things that we can do more later on in some other examples in the future. Okay, so this is OpenMP in general. Nothing much to add over here, but yeah, there is something I can discuss with you all. Okay, now in this particular example, okay, how can we try to optimize further? So we can actually try to use the schedule clause. Now bear in mind, there are schedule, you have a few. You have static, dynamic, and then you have a third option, which is here. So I will put this link in together with the video description. So at least you can do some reading over here. It's a blog by Zaka's Corner. I think the blogger put a very good explanation about OpenMP scheduling between static, dynamic, and guided. But we'll be focusing on static dynamic. So we can actually specify how the OpenMP takes different chunks of data. So static means, as the name implies, we take a fixed chunk for every iteration. Dynamic means you take a dynamic chunk in the sense that whatever available data for a chunk size available, you will take that. So it's a bit, there's no particular order for dynamic, all right? So if you apply, let's say if I were to apply a schedule static of 4, so I will pass this link. So the details are here. I would recommend you all to do some self-reading to understand it. It's very easy to understand this one. This example is pretty good over here. I mean, the explanation is pretty good over here. So if I were to apply this schedule static, because static here, we are using static because the computation is consistent. We are multiplying each cell and storing the answer into a corresponding cell. So each iteration is consistent, computationally consistent. If you try applying OpenMP in primes, then maybe you should use dynamic, because as you remember, in primes, the larger the number, the longer it takes to compute the prime. But in this case, all iterations are consistent, so we can use static. So let's say I put static, and let's say I want to, for each chunk, I take 500. Let's say I'm putting 500 here because of the second loop. So let's say if I do that, can I make the algorithm a bit faster now, or the performance of the code a bit faster? Let's see. Compile. Did I save the code? Yeah, I did save the code. Okay, compile, run. Okay, one thread is reading. Now all threads are computing. Done. Surprisingly, it took a bit longer time. So why is that so? So sometimes we have to also understand. So this is where we need to investigate. We need to see how the scheduling works. All right. So there might be some slight variation. So this is where you can try to try out different types of configuration to see which configuration gives you the best results. Okay. But normally this is more optimization side. Okay. You might probably get 1 or 2 half a second improvements and things like that, depending on the size of the data also. So if I try dynamic now, let's see if dynamic work any better or not. In this case, dynamic and static will not make any difference because the iterations, the computation per iteration it's similar. Okay, so in this case, it's probably going to be the same. Slightly better, 7.2 seconds versus 7.8 and 8 seconds in the earlier versions, but so marginally from 22 seconds to 21 seconds. So it's a marginal improvements in parallel time. Okay, so that's it. I mean, it's a brief video. Now, if you check online, because this is a nested loop. I mean, technically it's nested loop, but it's not really nested because we are not using the J for the computation over here. The J is just added just to increase the complexity. So in a proper nested loop where the I and J is used in each iteration, there is another option called collapse. But we don't use it here. I won't use it here because this will not work. This will cause an error. I put collapse and I put 2. Why I put 2? Because I'm combining 2 loops. I'm combining 2 loops into one single loop. Okay, I'm combining 2 loops into one single loop. This is useful if your number of rows is lesser than number of threads, but the number of columns is huge. So this is one example over here. Okay. So in this context, I would like to refer you all to this particular site. I will provide this link in the description also to the video and also the Moodle. So what happens is, okay, so this is what we did just now is exactly the same thing. We did Pragma OMP parallel. Maybe I can zoom in if I hear a bit. Okay, Pragma OMP parallel 4. It's a very simple operation, but you can see this is a classic nested loop because the I and J is used in each iteration over here. Okay, so thread 0 will take different rows. So we are parallelizing the outer loop here. So this is what we call as row segmentation. Okay, this is what we call as row segmentation. All right, then the problem is, let's say if you have 4 threads, but your outer loop is only 3 iterations, then the last thread is going to probably do nothing in a classical row segmentation workload distribution, unless you put a schedule dynamic there. All right, or schedule static. So if you may try to parallelize the inner loop and not the outer loop, but don't do that. That actually will cause a lot of performance issues. Okay, because you're trying to parallelize the columns rather than the rows. It's not a good approach. It's always good to parallelize from topmost to the topmost, and then you go downwards. So a better approach is to collapse the loops into one. So let's say this for loop I and J, you can actually combine it into one single loop where you call, this is possible, okay, this is possible. You call integer I and J declared to 0. I and J is less than 3 times 6. This is a row, columns, 18, and I and J plus plus, and then and how you access the I and J, you convert the 1D to 2D by taking the division and the remainder for each row and column. This works perfectly fine. Okay, you can, so this is how you do it manually, or you can make this automated. You can maintain this by calling the word collapse here. Pragma OMP parallel collapse. So Pragma OMP parallel 4 collapse does the same thing as this operation here. It converts your nested loop into a single loop without you having to manually convert the code. But don't do this for this example. In this example, the J is not used in the iteration over here. If you were to apply collapse here, you will get incorrect results. You can try and see. Okay, you can try and see. You will get a wrong results over here. Okay, so this one, the collapse, you can use later on and we do matrix multiplication and you want to parallelize it using OpenMP. So yeah, that's it for this code. So this week's lab is pretty straightforward, if you ask me. I think probably you can complete this in half an hour. All right, it's fun, but it's quite straightforward. There's no need to measure performance over here. There's no need to measure TP time and so forth. It's more of your just to get some hands-on work in OpenMP. Now, my advice to you all is, should you finish this lab on time early, please use the remainder time to parallelize your POSIX thread code application. I mean, for prime, sorry. Please use the remaining time to parallelize the prime search algorithm using OpenMP. Okay, so you have done OpenMP for prime search. Sorry, my apologies. Please ignore last statement. You have done POSIX threads for prime search in the previous lab activity. Try redoing it using OpenMP. Okay, that's where probably you might need to apply the Pragma OMP critical, which we discussed in the lecture. Okay, so give it a try and see. All right, so do some self exploration. We will employ you all to do this. It's for your own knowledge also, and that part is not assessed. Only the questions here are assessed in your lab for week 4. Okay. So I think that pretty much covers it for this quick video. I mean, it's relatively shorter than other videos. All right, so if you have any questions, you can always refer to your tutors and your lecturers for consultation. All right, so I'm going to stop sharing. I hope you have a good week ahead with the labs, and I'll talk to you all soon again in the next video. Okay, thank you. Goodbye.